Have you ever stared into the night sky and wondered whether the stars were watching you back? Whether beyond the quiet shimmer of starlight, something vaster, something deeper was unfolding? We often think of space as cold, distant, and silent, but it is also a stage for the most dramatic forces the universe has ever known. And of all the characters that roam this cosmic theater, none are more enigmatic, more feared, and more fascinating than black holes. This journey begins not at the edge of the universe, but at its center, at the very boundaries of our understanding. Because what if everything we see, everything we are, is not outside looking in, but inside looking out? What if we ourselves live not in a universe expanding into nothingness, but inside a vast, spinning black hole? That idea, once whispered at the fringes of science, has returned with new fire. And to understand why, we must first understand the nature of black holes themselves. Through the event horizon, entering the dark heart of the cosmos. Not the pull you feel when you drop a stone or the quiet force that keeps your feet planted to the ground, but a cosmic curvature of space-time itself. A dance between mass and geometry. The story of black holes starts where mass becomes so concentrated that space buckles and time itself begins to lose meaning. When massive stars reach the end of their lives, their outward pressure, driven by nuclear fusion, can no longer counteract gravity. The core collapses, and if the mass is high enough, it collapses all the way and past white dwarfs, past neutron stars, into something far stranger, a singularity, a point of infinite density wrapped inside an event horizon beyond which not even light can escape. From the outside, this event horizon looks like a dark sphere floating in space. But what lies beyond it? What happens to matter, time, and space inside this abyss? It's a question that has haunted scientists, philosophers, and storytellers alike. We used to think of black holes as monsters, cosmic vacuums devouring everything nearby, but the truth is subtler. Black holes aren't hungry. They don't pull things in with magical force fields. Instead, they simply exist where the geometry of space has folded so tightly that all paths lead inward. If you pass the horizon, you're not sucked in. You're simply moving forward, and in a black hole, forward means deeper. That brings us to the thought-provoking idea that kicked off this journey. What if that downward spiral doesn't end in destruction, but in rebirth? What if the singularity isn't the end of the road, but a gateway, a bounce, a transition? In black hole cosmology, our universe, the stars, galaxies, cosmic background, radiation, everything may be the inside of a black hole that formed in some larger parent universe. To wrap your head around this, imagine a Russian nesting doll of realities, a cosmos within a cosmos, spinning silently in the dark. Our Big Bang wasn't an explosion from nothing, but the rebound of matter compressed past its limit in a parent universe. The singularity never formed. Instead, space and time were twisted so tightly they rebounded outward, creating what we see today as cosmic expansion. And the place we call the beginning may actually be the other side of a one-way cosmic doorway. In 1915, he introduced general relativity, the astonishing realization that gravity is not a force, but the result of curved space-time. Mass tells space how to bend, space tells matter how to move. And in the equations of relativity, something unexpected emerged: black holes. But Einstein himself was skeptical of them. The singularities predicted by his theory seemed too extreme, too unphysical. He believed the math must be hiding some deeper truth. Today, we still wrestle with that. Because while general relativity tells us how black holes should behave, it doesn't tell us what happens inside them. That's where we reach the limits of our current understanding, where quantum mechanics and relativity clash and where something new must emerge. Let's return to the event horizon, the boundary beyond which nothing escapes. From the outside, time appears to slow as an object approaches this line. You'd never see it cross. It would simply freeze, fade, and vanish. But for the object falling in time marches forward. There is no wall, no moment of contact. Just the inescapable geometry of space-time funneling you inward, and the question remains, inward to what? Some theories suggest the center is a singularity. Others, like the Einstein-Cartan theory, propose that quantum effects, specifically the intrinsic spin of particles, create a repulsive force at extreme densities. Instead of crushing to a point, the matter rebounds. And that rebound might be a Big Bang. There's more than one kind of black hole. Stellar black holes form from dying stars and range from a few to dozens of solar masses. Intermediate mass black holes, a missing link suspected but not often confirmed, may form from the merger of many stellar black holes or the collapse of dense gas clouds. And then there are supermassive black holes, monsters millions or billions of times the mass of our Sun, found at the centers of galaxies, including our own. How do these behemoths form? No one knows for sure, but the fact that they exist and influence the very structure of galaxies tells us they are not anomalies, they are essential. And finally, we have the theoretical primordial black holes, possibly born in the early universe if they exist at all. Some theories even propose that dark matter might be primordial black holes. If so, black holes didn't just come after the Big Bang, they may have preceded it. Wormholes, those famous science fiction shortcuts, emerge naturally from the equations of relativity. A non-traversable Einstein-Rosen bridge connects two points in space-time, like the entrance and exit of a tunnel. In black hole cosmology, that tunnel leads from the parent universe into ours. Could such a wormhole ever be crossed? Probably not, unless negative mass exists, a strange form of matter that exerts anti-gravity. We've never observed it, but the universe hasn't ruled it out either. If such matter exists, it might make it possible to survive the journey. And if advanced civilizations exist, ones that have reached Type 3 on the Kardashev scale, harnessing the energy of entire galaxies, might they have learned how to create their own black hole universes? Might they live in custom-made realities beyond our reach and comprehension? It's speculative, but it's also profoundly exciting. As we move forward in this journey, the questions deepen. What did the James Webb Space Telescope see that reignited this idea? Why do some galaxies appear to rotate preferentially in one direction? How does this tie into the structure of our universe and the idea that it too might be spinning? In the next section, we'll explore the rotating black hole universe theory, what it is, where it came from, and why recent observations have given it new life. But for now, take a moment to consider this. If the universe truly is a black hole, then every time we look up at the stars, we're not looking out, we're looking in. Spinning realities, a universe born in rotation. We ended the last chapter with a striking idea that we may not be looking out into space, but rather into the interior of a cosmic engine, an immense, rotating black hole. If that sounds extraordinary, that's because it is. But the story doesn't end with that image. It begins there. The question is no longer simply whether black holes can birth universes. It's more precise now. Could our universe, with its stars, its symmetry, its silence, and its noise, have been born spinning inside a rotating black hole? To understand why this matters and how it fits together, we need to explore a theory that has moved from the sidelines of cosmology toward the center of serious discussion, the rotating black hole universe model. A bold extension of black hole cosmology that reinterprets the very origin of everything we know. In standard cosmology, the Big Bang is a singular event, an explosion of space itself from a hot, dense point some 138 billion years ago. From that first moment, the universe expanded rapidly, then cooled, forming atoms, stars, galaxies, and life. But for all its success in explaining observations, this model leaves some essential questions unanswered. Why did the Big Bang happen? What came before it? Why does the universe appear so finely balanced, flat, smooth, and structured? In black hole cosmology, the beginning is not a singularity in the traditional sense, but rather a bounce, a collapse, followed by expansion. And in the rotating variant of this model, it's more than a bounce, it's a spin-up. The parent black hole that birthed our universe wasn't static, it was rotating, and so are we. This theory builds on the idea that a black hole can carry angular momentum. In the language of relativity, this is known as a Kerr black hole, a rotating solution to Einstein's field equations first described in 1963. Unlike a simple Schwarzschild black hole, which doesn't rotate, a Kerr black hole twists spacetime as it spins, dragging nearby matter, and even light around with it, a phenomenon called frame dragging. Now imagine that this spinning black hole doesn't just exist in isolation. Imagine that within it, a universe is forming, a universe born with rotation embedded into the very structure of its spacetime. In 2023, the James Webb Space Telescope, JWST, captured images of distant early galaxies. These galaxies, among the first to form after the Big Bang, showed something strange, a preference in rotation. Approximately 2/3 were spinning clockwise. Only 1/3 spun counterclockwise. This wasn't what we expected. In a universe formed by random processes, we'd anticipate an even split. Galaxies should rotate in both directions equally like coins flipped by chance across the cosmos. But here was a statistical imbalance, a subtle yet significant hint that something about our universe had a preferred direction. Physicist Leor Shamir analyzed over 260 galaxies and found this discrepancy. While it has yet to be confirmed by other surveys, and some suggest selection bias may be to blame, the mere possibility has sparked renewed interest in black hole cosmology. Because if the universe was born inside a rotating black hole, then this preferred spin might not be an accident. It might be a signature embedded in the galaxies themselves. Let's zoom out both figuratively and literally. In the Kerr solution, rotation has profound effects. Not only does it alter the geometry of spacetime, but it also changes the causal structure of the black hole. Unlike non-rotating black holes, black holes contain an inner horizon, an ergosphere, and potentially even a passage through to another region of spacetime. From a cosmological perspective, rotation provides several fascinating advantages. A rotating black hole universe generates natural anisotropy, a slight departure from perfect symmetry, just like what we observe in the cosmic microwave background, CMB. Predicts a direction of time. The spin defines an arrow, possibly linking to the thermodynamic arrow of time we experience. Offers an internal engine. The centrifugal effects of rotation can counterbalance gravitational collapse, enabling the bounce that prevents a singularity. And here's where the connection gets eerie. The mathematics of such a rotating bounce generate conditions that closely mimic cosmic inflation, the rapid expansion theorized to occur in the early universe. In the standard model, inflation is added to solve problems like flatness, homogeneity, and the horizon problem. But in black hole cosmology, inflation emerges naturally from the dynamics of rotation and collapse. That's not a patch, that's a prediction. If our universe is the interior of a rotating black hole, what does that make the event horizon? From our side, it's the observable edge of the universe. But from the outside, in the hypothetical parent universe, it's a black hole's outer boundary cloaking a strange interior. And if the collapse didn't end in a singularity, but instead led to a bounce, then the matter that fell inward never stopped. It rebounded outward through what's called an Einstein-Rosen bridge, a non-traversable wormhole that connects two regions of space-time. Each black hole becomes a cosmic womb, birthing a new universe. Each new universe begins with its own laws, structures, and dimensions, but perhaps carries echoes of its origin encoded in its rotation, its geometry, and its quantum state. In this framework, our universe is a child, but it, too, may become a parent. Every black hole within our cosmos could harbor another universe beyond its own event horizon. It's a fractal vision of existence, universes within universes, each one spinning, evolving, birthing new realities beyond the grasp of the last. This leads to one of the most poetic and most haunting questions in cosmology. If our universe was born from a black hole in another universe, then where did that parent universe come from? And what about its parent? Does this chain continue forever? Are we just one in a potentially infinite hierarchy of embedded realities? And if so, is there an origin, a primordial universe, a first black hole? Or is it really turtles all the way down? We don't know. And that not knowing is part of what makes this theory so beautiful, because in exploring it, we're not just asking about equations and energy, we're asking about meaning, about place, and about the strange possibility that the truest boundaries of our universe are not distant galaxies, but the curved walls of a cosmic interior. Let's add one last speculative layer. If this theory holds and black holes birth new universes, then perhaps sufficiently advanced civilizations, those that reach Type 3 on the Kardashev scale, don't simply master energy, they master creation. They could, in theory, collapse matter in a controlled way to form artificial black holes, seeding new universes. Not as weapons, not as experiments, but as refuges. What if the solution to the Fermi paradox, the question of why we don't see evidence of alien life, is simply this: the most advanced beings have left. They've migrated into universes of their own design, universes better suited to their existence, universes they control from the inside. And we're the ones who stayed or were born here long after the architects had gone. It's a chilling, humbling possibility, but not a hopeless one, because it means that intelligence doesn't disappear. It evolves in ways we cannot yet comprehend. In the next section, we'll compare the rotating black hole cosmology model to the standard Big Bang model and ask where each excels, where they falter, and what new light they cast on the mysteries of inflation, dark energy, and cosmic structure. But already one thing is clear: this theory doesn't just reshape how we think about black holes. It reshapes how we think about the entire universe. Maybe we were never meant to escape black holes. Maybe we were born in one. Two origins, one universe, a tale of two cosmologies. So far, we've journeyed through the core ideas behind rotating black hole cosmology, a universe born not from a single explosive point, but from a collapse, a bounce, and a spin. But before we get swept up in the poetic allure of this alternative model, we must step back and ask, how does it compare with the reigning paradigm? The standard model of cosmology built upon the Big Bang theory has withstood the test of time for nearly a century. It describes an expanding universe that emerged from a hot, dense state predicted by general relativity and supported by a wealth of observational evidence. The cosmic microwave background, CMB, the abundance of light elements, the large-scale structure of galaxies, and the redshift distance relationship discovered by Hubble. So why challenge it? What gaps remain in the Big Bang story that invite other voices, like black hole cosmology, into the conversation? Let's explore the contrasts between the two. He's standard model posits a singular origin, a moment of infinite density and temperature from which everything emerged. It does not, however, explain why the Big Bang happened or what came before it. At T0, our equations break down. Time itself ceases to have meaning. It is quite literally the edge of understanding. In black hole cosmology, there is no such absolute beginning. Instead, the birth of our universe is interpreted as the interior evolution of a black hole formed in another universe. This is a bounce, not a beginning, an unfolding of compressed matter into a new cosmic arena. In this model, time doesn't start. It continues, or albeit in a radically different form. One story starts from nothing, the other from something else. One of the most successful additions to the standard model is cosmic inflation, a burst of exponential expansion in the first fraction of a second after the Big Bang. This idea explains three big puzzles. Why is the universe so flat? Why is it homogeneous across vast distances? Why do distant regions have identical temperatures even though they've never been in contact? Inflation solves these problems, but at a cost. It introduces a new energy field, a new particle, the inflaton, and parameters that must be finely tuned. By contrast, rotating black hole cosmology achieves similar results without adding new ingredients. The geometry of a rotating collapse, curved spacetime under torsion, naturally produces an inflation-like expansion during the bounce. In this framework, inflation isn't added on, it's built in. That elegance is seductive, but it must still be tested. Time is perhaps the most mysterious dimension we experience. In both models, the universe expands with time, but their treatment of time's origin is different. In standard cosmology, the arrow of time, the reason events unfold in one direction, is explained through entropy. The early universe was in a low entropy state, and entropy has increased ever since. But why did it start that way? Black hole cosmology offers a different lens. If our universe is the interior of a rotating black hole, then the arrow of time might be inherited from the parent universe. The spin and structure of the parent define the orientation of causality in the child. Time has a direction, not because of chance, but because of cosmic heritage. Both models agree that the CMB is a critical test. In the standard model, the CMB is the relic radiation from the hot plasma of the early universe, cooled to 27 K today and astonishingly uniform. Tiny variations in temperature on the order of microkelvin reveal the seeds of all structure in the cosmos. Black hole cosmology interprets these variations as signatures of the bounce and rotation. For instance, subtle asymmetries in the CMB polarization could indicate a preferred spin direction inherited from the black hole that birthed our cosmos. Recent high-precision data from Planck and other missions have found anomalies, dipoles, cold spots, alignment of multipoles that don't fit neatly into standard predictions. They don't prove black hole cosmology, but they whisper that something more may be at work. In the standard model, the accelerated expansion of the universe is driven by dark energy, a mysterious component that makes up about 70% of the cosmos. We know it exists. We don't know what it is. In black hole cosmology, this acceleration is a natural consequence of being inside a rotating, growing black hole. As mass continues to fall into the parent black hole, the volume of the interior universe grows. No extra field required, just a different point of view. It's as though our cosmos is inflating from the inside, not from an exotic vacuum energy, but from the continuing infall of matter in the higher dimensional world outside. Does this mean black hole cosmology wins? No, not yet. The standard model remains unmatched in its precision and predictive power, but it leaves open doors, questions it cannot answer, patterns it cannot explain. Rotating black hole cosmology doesn't close those doors. It steps through them and finds something waiting on the other side. A universe not just expanding but evolving through cosmic inheritance. A universe not born in isolation but part of a vast, possibly eternal chain of black holes and baby universes. It's bold, it's speculative, but it just might be true. Shadows and signals. Can we prove the black hole universe? We've walked the line between two grand visions of cosmic origin, the classical Big Bang and the bold elegance of black hole cosmology. The latter reinterprets the observable universe as the interior of a vast rotating black hole, its expansion structure and direction shaped by inherited properties from a parent universe. And it's compelling seductively so. But science doesn't thrive on poetry alone. It breathes through evidence. So we must now confront the uncomfortable question, how do we test this? How do we distinguish between metaphysical speculation and scientific reality? How do we look for the fingerprints of a parent universe from within the walls of our own? The path forward isn't smooth, but it is navigable. In 2016, a strange idea began to circulate in gravitational wave research. LIGO, which had recently detected the collision of black holes, a triumph in itself, had also registered anomalous echoes in the aftermath of some events. These faint delayed repetitions of the initial signal sparked whispers of something exotic, perhaps quantum structure at the edge of black holes, or even evidence that what we call a black hole might be more complex. Within the black hole cosmology framework, these echoes become something more. They might be reflections from the boundary of the universe itself, a sign that our cosmic horizon isn't just a limit of our view, but a real physical edge. A membrane, a wall. If that's true, then we're not just receiving whispers from dead stars. We're hearing the rumble of our cosmic container reverberations from the curvature of a larger dimensional reality. Still, critics rightly urge caution. These echoes are weak. Controversial, not universally observed. The signal could easily be noise, and multiple follow-up studies have failed to replicate the findings consistently. But like a knock in the dark once heard, it's hard to ignore. We explored one of the most fascinating and polarizing observations from the James Webb Space Telescope, a disparity in galactic rotation. According to physicist Leor Shamir's analysis, early galaxies appear to spin with a directional bias. Roughly 2/3 rotate clockwise, and only 1/3 counterclockwise. This imbalance isn't predicted by standard cosmology. In fact, it should be impossible if the universe had no preferred direction at birth. To black hole cosmologists, this anomaly isn't an error, it's a clue. A spinning parent black hole could imprint that preferred rotation on its internal space. The distribution wouldn't need to be perfectly even. It would tilt, twist, spiral. But is this a real effect or an artifact of limited data? Shamir's study looked at a few hundred galaxies, a statistically meaningful sample, but still vulnerable to selection bias. Other surveys have not found the same asymmetry. The result, while electrifying, remains unconfirmed. It stands as a testable prediction, a challenge, and a reminder that all new theories live under the microscope of skepticism. In theoretical physics, white holes are the mirror image of black holes, regions that matter and energy can exit but never enter. In the black hole cosmology model, the Big Bang itself is reinterpreted as a white hole event, the expulsion point of matter from a black hole in a parent universe. But here's the catch: we've never seen one. There are good reasons for this. White holes, if they exist, are probably short-lived and violently unstable. Their existence requires conditions we don't see in nature. Yet if our universe really began as a white hole, shouldn't there be some leftover trace, some relic, however faint? At the moment, no such evidence has been found. The model predicts that we wouldn't be able to observe the white hole directly. It would lie before our observable time, but that doesn't make it immune to critique. Critics argue that redefining unobservable phenomena is a dangerous game. The model must make falsifiable predictions or risk drifting into the realm of unfalsifiable metaphysics. The cosmic microwave background remains one of the most powerful tools in cosmology, a picture of the infant universe frozen in time. And perhaps it holds the key to resolving this debate. If our universe spun at birth, the CMB should carry that twist. We should see anisotropies, alignments, and polarization patterns that betray rotation. Indeed, some studies of the CMB, particularly those examining the so-called axis of evil, have hinted at large-scale alignments inconsistent with a purely isotropic universe. But interpretation remains murky. Are we reading deep truths in the CMB, or playing connect the dots with cosmic randomness? New missions, better data, and sharper instruments may one day tell us. To elevate black hole cosmology from hypothesis to theory, we need clear, testable predictions that differ from the standard model, repeatable, high-precision observations that support those predictions, mathematical models that don't just explain anomalies but predict them before they're observed. Gravitational wave astronomy may be the key. Upcoming missions like LISA, set to launch in the 2030s, will detect gravitational waves with unprecedented sensitivity. If echoes persist, or if we detect waves that align with internal bounce models, black hole cosmology will step out of the shadows. Similarly, quantum computing and analog gravity experiments may allow us to simulate the boundary behavior of black holes and test the holographic principle in new ways. And finally, AI-aided pattern recognition in cosmic background data may spot what human eyes miss. Black hole cosmology is not yet confirmed, but nor is it merely fantasy. It stands at the threshold between imagination and insight, compelling, controversial, and incomplete. Like all great theories before it, it asks us not just to look harder, but to look differently. It tells us that perhaps the edge of the universe is not a horizon, but a surface, not a limit, but a membrane, not a void, but the interior of something larger. And if it is correct, the proof may be drifting toward us even now, quiet ripples in the dark, waiting to be heard. Universes and the nature of existence. In black hole cosmology, our universe is not a standalone creation. It is the interior of a rotating black hole formed in another universe, a daughter universe, so to speak. This black hole collapsed under its own gravity, compressed matter and energy to extraordinary densities, and then, through mechanisms like torsion or quantum effects, triggered a bounce. That bounce didn't return to the parent universe. It unfolded inward, creating a new expanding spacetime. And we live in that inward unfolding. But it doesn't end there. Just as our universe was born from a black hole, the theory suggests that black holes within our universe may do the same. Each one, if the conditions are right, may give rise to its own universe, hidden behind its event horizon, its contents forever inaccessible from our side. The result is a fractal cosmology, a universe of universes, a cosmic matryoshka doll of reality, each layer embedded in the last, each with its own physics constants and potential for complexity. This idea echoes ancient myths, the world upon the back of a turtle, standing on another turtle, and so on all the way down. But in this modern reimagining, the turtles are black holes, and they might go all the way up too. Inevitably, we're drawn to ask, where did it all begin? If our universe was born from a parent black hole, where did that parent universe come from? Was it born from yet another black hole, and that one, and that one? Does the chain go back forever? This is the cosmic equivalent of the chicken and egg problem raised to infinite dimensions. In one view, there is no first universe, just an eternal lineage of cosmic births and rebirths governed not by divine intervention or absolute beginnings, but by recurring physical processes. But in another possibility, there was a first, a primordial pavement universe, the originator of all others. Perhaps this universe didn't form from a black hole. Perhaps it formed black holes that gave rise to others. It might have been vastly simpler or incomprehensibly complex. Or maybe, just maybe, it was created on purpose. Some theorists, including futurist thinkers like John Michael Godier, have explored the notion that sufficiently advanced civilizations might gain the ability to engineer black holes and thus create universes. Think about that. If civilizations could control the parameters of these artificial black holes, mass rotation charge, they might influence the initial conditions of the resulting universe. They could, in theory, design universes optimized for stability, complexity, or even life. Like gardeners planting new gardens not on planets, but across space-time itself. And if that's the case, our universe might not just be a child, it might be an engineered offspring, tailored, fine-tuned, and set spinning by hands or minds we cannot yet imagine. This possibility reframes everything. It suggests that the fine-tuning we observe in the laws of physics, the precise values of fundamental constants that make atoms, chemistry, stars, and life possible, might not be a coincidence or a mystery. It might be a legacy. We might exist because someone or something intended us to. If so, where are they? Where are the architects, the creators, the advanced civilizations that supposedly seeded the black hole from which our universe bloomed? One answer is chilling in its logic. They've moved on. Once a civilization attains the ability to create its own universe, its own ideal cosmos, why remain in this one? Why not construct a new universe with more favorable physics, richer energy, states, fewer limits? Why not enter the very black hole they create, migrating to a realm of their own design? This becomes a potential answer to the Fermi paradox, the riddle of why we see no evidence of alien civilizations. Perhaps the most advanced beings don't leave artifacts, they leave the universe. And in their place we find silence. But not emptiness, because in that silence, life begins again. For all its physics, black hole cosmology evokes a sense of something greater. It doesn't demand belief in a God or an afterlife or a soul, but it does whisper that our universe is not alone, and neither are we. It suggests that consciousness may not be a fluke, but a pattern, an emergent behavior that arises in many universes across many horizons. It invites us to see ourselves not as cosmic accidents, but as cosmic descendants born of a long lineage of realities, each giving birth to the next, not unlike life itself. In this model, death is not an end. Collapse is not defeat. Every black hole is a potential beginning, every boundary a doorway. If black hole cosmology is true, we live inside a structure far larger, older, and more dynamic than we've ever imagined. But even if it is not, if future experiments disprove it, we've still gained something precious. We've learned that the universe is open to imagination but tethered by reason, that it invites questions even when it withholds answers, and that every time we think we've reached the edge of knowledge, we find not a wall, but a mirror reflecting our own desire to understand. Never assume the sky is the limit. The edge of the universe might just be the start of another. And if it is, then the most human thing we can do is to keep wondering what comes next. Beneath a starlit sky, where the hush of night settles over the earth and each shimmering point of light trembles with ancient fire, one cannot help but wonder what lies beyond. Every star is not merely a distant sun, but a portal into the unfathomable, the grand celestial unknown where reality bends and mystery reigns. This is the threshold where questions take root. What is our place in the universe? Why does it behave in ways that defy our best theories? What secrets lie curled within its deepest shadows? The cosmos, silent and unyielding, challenges us not with violence but with enigma. From the earliest human skywatchers charting stars with bare eyes to today's theorists manipulating the language of quantum fields, we have always sought to pull back the curtain of the night. But the more we discover, the more the void seems to whisper. What if the anomalies we observe, those strange alignments, fading stars, and silent signals are not merely noise in the data, but the universe itself, speaking in riddles we have yet to learn how to read? To stand beneath the stars is to stand beneath a mystery that grows deeper the more we illuminate it. The universe, once thought to be a tidy, expanding field of matter and energy governed by elegant laws, now reveals itself to be full of quiet rebellions against order. Consider the light that has traveled for billions of years to reach us, its journey long and tireless, weaving through dust, gravity wells, and magnetic fields only to arrive as a whisper on the lens of our telescopes. In that whisper lie secrets, background noise that isn't noise, variations that shouldn't exist, alignments too precise to be dismissed. The cosmic microwave background, for instance, was once considered the ultimate proof of a smooth, isotropic universe born from a hot Big Bang. But even it holds a dissonant note, a peculiar alignment known ominously as the axis of evil, where temperature fluctuations in the CMB appear to line up along the plane of Earth's orbit, violating the assumption that the universe should look roughly the same in all directions. Is this a cosmic coincidence? A statistical quirk? Or something far more profound, a fracture in the symmetry of space-time itself? This anomaly, undeterred by new instruments and refined data, endures. It raises questions not just about the early moments of the cosmos, but about whether our position within it is as ordinary as we once believed. It challenges the cosmological principle, the idea that no place in the universe is special, but what if it is? Other anomalies compound the puzzle. The dipole repeller, a vast region of space with an apparent gravitational push, defies intuition. It is not an object, not a cluster of mass, but rather a void, a sprawling absence that reshapes the trajectories of galaxies, guiding their flow not with attraction, but repulsion. While the great attractor draws matter toward it with an invisible hand, the dipole repeller seems to sculpt galactic motion in the opposite direction, as though the universe itself breathes in and out across inconceivably large scales. What could give emptiness such force? The mere existence of such a repulsive influence suggests that gravity, our most familiar of cosmic forces, may behave in ways we do not fully understand when confronted with true emptiness. Or perhaps it is not gravity alone at play, but dark energy or some other force not yet woven into our equations. These vast structures or anti-structures mock our instincts about cause and effect, pull and push, presence and absence. They dance just beyond comprehension, shaping the destiny of galaxies as if by phantom touch. And there are trails, like fingerprints left behind after celestial collisions, ghostly streams of stars, stretched across the sky in delicate, fading arcs. Speak of ancient galactic mergers, tides of destruction and rebirth played out on unimaginable timescales. These galactic ghost streams are not merely beautiful, they are memory given form. They drift silently through the cosmos, so faint that even our best instruments strain to detect them. They are what remain after a smaller galaxy is swallowed by a larger one, its stars torn and scattered, leaving behind glowing trails like the long sigh of something once whole. The Sagittarius stream in our own Milky Way is a haunting example, a whisper of a past collision still echoing through our spiral arms. These structures offer history lessons, not written in books, but in gravity and light. They remind us that the cosmos is not static, not serene, but kinetic and violent beneath its tranquil veneer. Yet these same trails also blur the edges of our understanding. Some do not conform to our models of gravitational dynamics. They twist and stretch in ways that suggest forces unaccounted for, or events beyond the bounds of prediction. They force us to look not just outward, but backward, trying to piece together a puzzle scattered across billions of years and billions of stars. Even the brightest lighthouses of the cosmos seem to conspire in mystery. Quasars, brilliant, ancient engines of energy surrounding supermassive black holes, are not merely distant beacons. They carry hidden messages in their light. Their radiation, when filtered through our instruments, shows signs of polarization, waves of light aligning in directions that, across billions of light years, should be random, yet they are not. Patterns have emerged, alignments stretching across vast swaths of sky, as if entire constellations of quasars had somehow synchronized their polarizations. What could cause such coherence across such distance? Some theorize that intergalactic magnetic fields have bent their light over time, imprinting an unseen structure onto the cosmos itself. Others suggest that these alignments are fossils' imprints of primordial conditions, frozen into the scaffolding of the universe at the moment of its birth. Or perhaps they hint at something even more radical, that space-time, on the largest scales, is woven with hidden symmetries, echoing patterns that transcend galaxies, epochs, and comprehension. Here again, we are left with signals we can observe, but not fully explain a Morse code tapped out by the stars that we have only just begun to translate. Even closer to home, the solar system harbors its own enigmas. Beyond Neptune lies the Kuiper Belt, a frozen hinterland of icy remnants from the solar system's formation. It should, by all accounts, stretch smoothly outward into the void, gradually thinning, yet at a distance of about 50 astronomical units. The distribution of objects drops off sharply a cliff in space known simply as the Kuiper Cliff. Why, what truncates the solar system so precisely? Could it be the gravitational influence of a hidden planet, an as yet unseen Planet 9 lurking in the cold, dark beyond, or is it a relic of the solar system's chaotic infancy, shaped by migrations of the gas giants and scattering collisions that cleared the outskirts like broomstrokes in dust, whatever the cause? This cutoff speaks of an invisible boundary, a line the universe itself seems to have drawn at the edge of our planetary domain. It is both a limit and a dare, calling us to cross it and find what lies on the other side. Far stranger still are the voices from the deep, Fast radio bursts, blindingly quick flashes of radio energy have confounded astronomers since their discovery. Some last only milliseconds, yet carry as much energy as the sun emits in days. Many come from distant galaxies, their origins veiled, their mechanisms unknown. Some repeat, some do not. A few have been traced to magnetars, highly magnetized neutron stars whose fields are so strong they can twist atoms and erase data from spacecraft from thousands of miles away. These cosmic monsters, born in the death throes of giant stars, are engines of energy and chaos. Their quakes can ripple spacetime. Their emissions reach across the stars. And yet their numbers are so few, only dozens known, that each new discovery reshapes our understanding of stellar death and high-energy physics. Could they be the source of these eerie bursts? Or do we still lack the key to understanding these signals, which seem to come from everywhere and nowhere, whispering a message we can hear but not yet decipher? And then there are the silences, the empty spaces that speak louder than noise, intergalactic voids, cosmic deserts where galaxies thin and then vanish, where gravity goes quiet and the light dims. Some of these voids are so vast that entire superclusters could drift through them without ever meeting another galaxy. Yet they are not nothing. They hold dark energy, magnetic fields, perhaps even unknown particles. Signals have been detected from within these voids, strange, persistent radio waves from regions where no galaxies dwell. Could these be echoes of ancient collisions, the death cries of long-vanished structures, or something entirely other? Phenomena born in isolation, beyond the reach of our frameworks. The universe does not offer us clean conclusions. It offers us riddles, wrapped in starlight, pulsing through the radio dark, folded into patterns of gravity and electromagnetic hush. For all our equations and models, for all our machines perched on mountains or circling Earth in the cold void, we remain in the infancy of cosmic comprehension. These anomalies, these strange behaviors and misbehaving lights, do not close the book of science. They open it. They remind us that the universe is not only grand, but layered with meanings we do not yet possess the language to describe. In every unexplained alignment, every vanished star, every echo from nowhere, we hear it again, the whisper in the darkness that says, "Keep going. There is more. There is always more." And in that whisper, fragile and fleeting, is the truest music of the cosmos. Not silence, not certainty, but wonder. Cosmic alignments and recoiling voids. Imagine drifting through the void, beyond the veil of stars, where silence reigns and the laws we once thought immutable begin to tremble. Out there, far from the warmth of the familiar, the universe whispers not in words, but in alignments, patterns, and movements subtle, defiant signatures that unsettle the very foundation of our cosmic understanding. This part of our journey ventures into a realm of disquieting mystery, where two anomalies rise not with thunder, but with an eerie, quiet defiance, the axis of evil and the dipole repeller. These are not characters of myth, but signatures etched into the cosmic canvas, challenges to the assumptions that have guided generations of cosmologists. They speak to us from the deepest stretches of space, not with clarity, but with riddles that make us question whether the universe we inhabit is as random and isotropic as we once believed, or if some vast and hidden architecture awaits discovery just beyond the limits of our perception. As we peer into the relic radiation of the Big Bang and trace the silent flows of galaxies, we begin to see something uncanny, alignments that should not exist, and empty places that push the cosmos itself. In this search for meaning, the line between science and wonder begins to blur, as we confront the unnerving possibility that there may be forces and forms at work that remain cloaked, not only in distance, but in a silence deeper than space. It begins with light, not the ordinary kind that flits through windows or reflects off water, but the most ancient glow, the afterimage of creation itself. The cosmic microwave background, or CMB, is our universe's baby picture, a relic radiation imprinted on the fabric of space some 3,000 years after the Big Bang. It is faint, cold, and nearly uniform, a soft hiss of microwaves whispering from all directions, a cosmic lullaby that lulled astronomers into thinking the universe was well-behaved on large scales. The cosmological principle, the idea that the universe, averaged over vast distances, looks the same in every direction, was long held as a guiding assumption, a bedrock of cosmology. But then came the anomaly, an unsettling smudge in the data, a pattern that refused to fade. First detected by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite. A curious alignment appeared in the CMB's temperature fluctuations, stretching across the sky along a particular axis. This unlikely alignment, statistically improbable and persistently present, soon earned a provocative name: the axis of evil. Its moniker, coined half in jest, captured the discomfort it stirred among scientists. Here was something that shouldn't be: a crack in the elegant symmetry of the cosmos. The axis aligned suspiciously with the plane of Earth's orbit, an alignment that raised the possibility of measurement bias or local contamination. Yet attempts to scrub it away through modeling and corrections only seemed to confirm its tenacity. Like a shadow that won't dissolve in the light, the axis lingered, suggesting a directional preference in the oldest light. We have an affront to isotropy, and perhaps to simplicity itself. The axis of evil confronts us with more than just a glitch. It threatens the philosophical underpinnings of cosmology. If the universe has a preferred direction, if the oldest photons we can see are etched with asymmetry, then the very idea of a uniform cosmos falters. Theories abound to explain it. Some posit that the anomaly is an observational artifact, a statistical fluke born from our single vantage point within a vast multiverse. Others propose that we're glimpsing the aftershock of something immense, perhaps a collision with another universe, one that grazed our own like a ghost ship scraping the hull of reality. More speculative still are hypotheses involving primordial magnetic fields or unknown forms of anisotropic dark energy that might have imposed structure on the infant universe. In each case, the axis of evil invites not comfort, but vertigo, a sense that we're standing on the edge of an unfinished story whose ending we are not yet meant to read. And yet, for all its menace, it also ignites the flame of curiosity. What if this anomaly is not a problem, but a clue? What if it is not an error to be corrected, but a signal, however faint, that we are glimpsing the deep scaffolding of the cosmos, a design far stranger and more deliberate than we have ever dared imagine? As our gaze shifts from the relic light of the early universe to the present dance of galaxies, we encounter a second anomaly, equally silent and equally defiant. The dipole repeller is not a glowing beacon or a gravitational anchor. It is an absence, a void with invisible hands, unlike the axis of evil, which unsettles the heavens with its alignment. The dipole repeller exerts its mystery through motion, galactic motion. In the cosmic sea, galaxies are not stationary islands. They flow, pulled and pushed by the uneven distribution of mass. For decades, astronomers noticed that our local group of galaxies was moving at an unusually high velocity relative to the CMB, pulled in part by a massive concentration of galaxies known as the Great Attractor. But this pull was not the whole story. The trajectory of motion required something more, an unseen push. In 2017, astronomers analyzing the Cosmic Flows 3 survey discovered that our motion was not only due to gravitational attraction, but also to repulsion. They identified a vast, underdense region of space, a void with enough gravitational contrast to repel galaxies. This ghostly absence became known as the dipole repeller. Unlike the Great Attractor, the dipole repeller cannot be seen in traditional images of the sky. It is a structure of inference, known not by what it emits, but by how it shapes the flows around it. Galaxies flee from its coordinates, their motions echoing the contours of gravitational imbalance. It is, in essence, a negative space whose influence rivals that of the densest clusters. And therein lies the paradox. How can emptiness exert a force? The answer lies in the subtleties of gravity on cosmological scales. Dense regions pull, but voids, being less dense than their surroundings, create gradients that effectively push. It is not a repulsion in the electromagnetic sense, but a gravitational choreography, a recoiling dance that emerges from contrast. The dipole repeller is a sculptor of galactic paths, a silent architect shaping the universe not through presence, but through absence. And like the axis of evil, it raises profound questions about the structure and origin of cosmic flows. Are these alignments and motions mere accidents, or are they echoes of deeper laws, hidden dimensions, or a history we have yet to uncover? Together, the axis of evil and the dipole repeller frame a haunting question. What if the universe is not isotropic, not homogeneous, but instead patterned by unseen forces and fossil scars of primordial events? What if voids and alignments are not quirks but keys? Keys that unlock doors to a pre-inflationary universe, to entanglements between our cosmos and others, to a topography of space shaped not only by mass and energy, but by conditions we cannot yet measure. In these questions lies the emotional weight of cosmology, the tension between what we observe and what we believe. These anomalies do not merely tweak equations, and they invite a reimagining of the universe as a place not of serene uniformity, but of dynamic asymmetry, of hidden engines that propel galaxies and stretch the very fabric of space. It is humbling to consider that our most powerful tools, satellites, surveys, simulations, still illuminate only fragments of the grand design. Each new map of the sky is like a lantern in a cathedral, revealing frescoes too vast to grasp, too dim to decipher in full. And yet we are driven onward, not because we expect closure, but because each anomaly is a promise that the universe still has stories to tell. The axis of evil and the dipole repeller are whispers from the edge of comprehension, subtle deflections in the script of space and time. They are reminders that reality is not always polite, not always symmetric, not always predictable, but it is beautiful, melancholically beautiful, because to witness the universe in its mystery is to be part of something that endlessly outpaces us, that invites us to reach, even when we cannot grasp. The great irony is that these vast structures, the axis stretching across the sky, the repeller lurking in the abyss, are discovered not with our eyes, but with patience, mathematics, and an unyielding faith that patterns, however faint, can be found. And so we search, measuring polarization angles, mapping redshifts, constructing gravitational velocity fields like cartographers of an unseen continent. In this work, cosmology becomes more than science. It becomes a kind of pilgrimage, a journey toward the hidden harmonies of the universe. Perhaps one day, with more precise instruments and deeper theories, we will see not just the shadows, but the causes behind them. Perhaps we will trace the axis to a bubble wall in a multiverse sea, or understand the repeller as a relic of topological variations seated in a pre-quantum epoch. Or perhaps we will find only deeper puzzles, each answer birthing a new mystery in an infinite regress that mimics the very expansion of space. But even then, we will not have failed, for the goal is not to end the mystery, but to expand the horizon of the known. These anomalies, these trembling irregularities in the fabric of the cosmos, are not cracks in science, they are its frontier. They call us forward, into the deep, into the cold, into the silence where stars align and voids breathe. And in that silence, we listen. We listen for the shape of what is still to come. Echoes of galactic memory, streams and light patterns. Imagine drifting in the silence between galaxies, where time slows and ancient light whispers across the dark. In this inky canvas, there exist traces so faint they nearly escape the eye. Tenuous, gossamer trails stretched across millions of light years like the fading footprints of celestial giants. These are the galactic ghost streams, ethereal remnants of ancient galactic collisions, the long-forgotten relics of cosmic cannibalism and gravitational entanglement. They do not blaze across the cosmos like quasars or erupt in cataclysm like supernovae. Instead, they linger, delicate and spectral, formed when galaxies brush too close, ensnared by each other's gravity in a silent, slow-motion dance that ends with one devouring the other, as stars are stripped from their hosts and slung into the void. They form ribbons of stellar debris, haunting monuments to mergers that took place eons ago. These streams are like faint murmurs of memory, barely perceptible against the glow of the galactic night. And yet they hold stories of breathtaking violence and transformation to the naked eye. They are invisible to astronomers with deep sky surveys and wide-field infrared telescopes. They are fragile stitches in the cosmic fabric, hinting at episodes of upheaval that reshape the architecture of entire galaxies. Among them, the Sagittarius stream in our own Milky Way stands out, a sprawling loop of stars torn from a dwarf galaxy as it was gradually consumed by our galactic core. Like a ghost circling its grave, it arcs across the night, testifying to a time when our galaxy was not a quiet spiral, but a predator in a stellar jungle. Detecting such streams demands more than technology. It requires patience, serendipity, and a relentless willingness to chase shadows. The stars within these streams do not burn brighter than their neighbors. They do not cry out. Their arrangement is their only clue, elongated, curved, whispering of orbits stretched by tidal forces, of gravitational embraces that reached across space and time. Long exposures, motion tracking, and digital sky surveys piece together these faint threads, revealing more of them with each passing year. And what they tell us is astonishing. The universe is not a static mosaic, but a dynamic, ever-evolving structure. Galaxies grow not just by birthing new stars, but by consuming one another, merging and assimilating in processes that take billions of years yet leave behind unmistakable scars. These ghost streams are fossils, and astronomers have become their paleontologists, reconstructing the family trees of galaxies from their long-lost limbs. Sometimes, the cannibal is not even the predator. Dwarf galaxies swept into larger hosts may themselves have devoured smaller companions in their own pasts. Each stream becomes a layered story, a branching history of creation and consumption. But not all cosmic memories are drawn in stars. Some are encoded in light itself, etched into the oscillations of electromagnetic waves traveling across unimaginable distances. Enter the quasar, among the most powerful and luminous objects in the universe. At the center of distant galaxies, supermassive black holes feast on infalling matter, releasing torrents of energy as they spin and blaze with the light of unmaking. These quasars are beacons from the early universe, some shining across the abyss for more than 10 billion years, yet their brilliance is not their only wonder. As their light journeys toward us, it becomes subtly polarized, its waves aligned in particular directions. Normally, light vibrates in every plane perpendicular to its path, chaotic and free, but when it interacts with magnetic fields, gas clouds, or dust, it becomes ordered, filtered. What's astonishing is that quasar light across billions of light years appears not only polarized, but aligned in ways that defy explanation. These polarization vectors, separated by cosmic gulfs that should render them independent, seem to point in similar directions, as if the universe itself is organizing the orientation of light. This phenomenon, so statistically improbable it borders on the uncanny, suggests that something deeper is at work, something embedded not in the quasars themselves, but in the intergalactic medium, in the very geometry of space-time, or perhaps in a primordial memory etched into the universe's infancy. What could cause such coherence on such enormous scales? Magnetic fields stretching across intergalactic space might subtly twist the light as it passes through, like ancient weavers guiding cosmic threads through invisible looms. These fields, though weak, can impose directionality over eons and distances, shaping the quasar's light into subtle patterns. Alternatively, the light may be passing through cosmic filaments, massive tendrils of dark matter and gas that form the scaffolding of the cosmic web. These structures could act as vast, anisotropic lenses, rotating and aligning light as it threads through them. Or perhaps we are seeing something even more profound, a fossil of the universe's initial conditions, a leftover ripple from inflation, frozen into the polarization of photons born in an earlier epoch. That these alignments might reflect some deep asymmetry in the fabric of the cosmos calls into question our assumptions about its isotropy, that it is the same in all directions. If this uniformity breaks, even in the subtlest ways, then our models must be revised, and the map of the universe redrawn. Quasar polarization may sound like a technical footnote, but it strikes at the heart of cosmology. These beacons, scattered across the cosmos, become a new kind of telescope, a way to look not at things, but through them, into the forces and fields that structure the universe. And yet, like the ghost streams, they are elusive, their light is faint, their signals buried in the noise of the cosmos. Detecting and measuring polarization with accuracy requires specialized instruments. Polarimeters capable of measuring the angle and degree of alignment with extraordinary precision. Observations must account for intervening dust, galactic emissions, and the vagaries of atmosphere and telescope. And yet, when these barriers are overcome, the patterns persist. Alignments emerge not in isolated regions, but across hemispheres, across epochs. The message, if there is one, is subtle but persistent. Something is shaping the light from the edges of the observable universe, something coherent, something large, something unknown. Together, ghost streams and quasar polarization form a kind of cosmic symphony, two very different melodies, each echoing across time and space, each whispering of hidden histories. One tells of gravitational violence and mergers past, the other hints at a lattice of invisible forces that shape light itself. They are not random curiosities, but pieces of a puzzle, suggestions that the universe contains an architecture we have barely begun to grasp. Perhaps there are relic symmetries from a time before stars, before galaxies, signatures from a deeper layer of physics that ripple upward into the structures we now observe. Perhaps these patterns reflect a universe that is not just expanding, but evolving toward complexity, toward coherence, toward something intelligible. Or perhaps they are signs of our own limitations, our anthropic perspective peeking through the veil, imposing order where there is only chaos. And yet, the data remains. The stars are there, the light is aligned, and the streams persist, drifting slowly like the last breath of something long gone. In this interplay of gravity and light, in the faint scars and luminous alignments, we glimpse a kind of galactic memory, a memory not made of neurons or thoughts, but of trajectories, distortions, and waveforms of the gravitational scripts galaxies follow, and the radiant signatures left in their wake. These memories are not conscious, but they are legible. They are inscribed across billions of light years, carried by stars and photons alike, waiting for minds patient enough to decode them. The cosmos, it seems, remembers not in stories, but in structure, not in words, but in wavelengths, and in that remembrance, we find both wonder and humility, for we, too, are part of this great memory. We are stardust reorganized into sentience, fleetingly aware of the ancient forces that shaped us. We look up, and in the light from distant quasars, in the wisps of ghostly star streams, we recognize something familiar, an echo of becoming, a fragment of a larger tale. And perhaps that is the greatest mystery of all, that the universe, vast and ancient and indifferent, speaks in patterns, and that we, ephemeral as we are, can still learn to listen. Perimeters of the known, the Kuiper Cliff, and the magnetar enigma. At the edge of everything we know, where the warmth of the sun fades into a pale glimmer and solar winds no longer blow with strength, there exists a silence that speaks of unresolved riddles beyond Neptune's orbit, where the Kuiper belt sprawls like a frozen debris field circling the sun. Astronomers once expected a steady population of icy remnants fossils from the solar system's formation to stretch far into the darkness. Yet, just past 50 astronomical units, something inexplicable occurs. The Kuiper belt abruptly ends, this stark drop in the number of objects, now hauntingly known as the Kuiper Cliff, is not a gentle fading away but a sudden plunge. As if the cosmos changed its mind, no clear gradient, no slow diminishment, only a conspicuous emptiness where once there was anticipated abundance. It is a cosmic cliff edge where possibility falls into silence. What could have swept this region clean, or never allowed it to form at all? Some suggest the gravity of a distant, undiscovered planet, Planet 9, lurking far beyond our telescopic reach, pulling on icy bodies and warping their orbits into hidden pathways. Others propose that early migrations of Jupiter and Saturn, or ancient interactions with rogue stars, sent gravitational shock waves through the solar nursery, scattering debris like leaves in a storm. Still others argue that this edge is simply where the primordial protoplanetary disk faded into nothing, a natural outer boundary of the sun's original birth cloud. But none of these theories fully satisfy the abruptness, the precision, the mystery of the cliff. It remains an open question in planetary science, a glaring omission in an otherwise elegant model. This outer boundary is not just spatial, it is epistemological. The Kuiper Cliff defines not only a limit to where most trans-Neptunian objects dwell, but also to how far our current understanding can stretch before it falters. Spacecraft like Voyager and New Horizons have slipped into this realm, sending back ghostly portraits of icy dwarfs and lonely rocks, hinting at a frontier that remains largely unexplored. Here, our maps become probabilistic, our models wobble. The expected fades into the enigmatic. We are reminded that the solar system, for all our charts and probes, still keeps secrets in its outermost shadows. It is at these margins that our theories reveal their gaps, and we encounter the humbling truth that we are still, in so many ways, beginners. The Kuiper Cliff is not a final line, but an invitation, a question mark drawn in the cold, urging us to peer deeper, to search with sharper instruments, and to rethink the assumptions we have taken for granted. It is a gentle mystery, quiet in its challenge, yet profound in implication. If our solar system has such abrupt structural features we have yet to explain, what of other star systems? What of the galactic edge? What unseen forces shape the perimeters of the known? But as we contemplate the icy silence of the outer solar system, a radically different anomaly roars from across the void, an explosion of force and mystery found not in the cold, but in the crucible of stellar death, deep in the galactic graveyards. Among the remnants of supernovae dwell the magnetar's neutron stars with magnetic fields so intense they make even the strongest laboratory magnets seem like toys. These compact cores, only a dozen kilometers wide, yet holding more mass than our Sun, are the densest forms of matter known outside black holes. But some neutron stars go even further. A rare few evolve into magnetars, their magnetic fields 1,000 times stronger than typical neutron stars, reaching intensities that defy comprehension enough to warp atoms, crack open the crust of the star itself, and potentially rip the very fabric of space-time. These celestial monsters do not whisper their presence. They shriek, with sudden gamma-ray flares and bursts of high-energy X-rays. They unleash tantrums so powerful they can be detected across galaxies. In 2004, a magnetar in our Milky Way SGR 180620 emitted a flare so intense it briefly altered Earth's ionosphere. Despite being 50 light-years away, had it been closer, it might have fried our satellites or even our atmosphere. These eruptions are believed to stem from starquakes, sudden rearrangements in the crust of the neutron star. Driven by the immense stress of magnetic pressure, it is as if the magnetar itself struggles under the weight of its own internal chaos. But magnetars are not merely loud, they are elusive. Their lives are short, their births rare, and what they might be telling us could extend far beyond neutron star physics. In recent years, a tantalizing connection has emerged between magnetars and fast radio bursts, FRBs, brief, millisecond flashes of radio energy from distant galaxies that once defied all classification. The mysterious nature of FRBs, some repeating, others not, had fueled wild speculation alien technology, decaying cosmic strings, echoes of black hole mergers. Then, in 2020, an FRB was traced to a known galactic magnetar, suggesting a concrete astrophysical source for at least some of these phenomena. Yet even this apparent clarity deepens the enigma. How can such short, sharp signals arise from something so massive, so dense, so slow by comparison? What does it mean that magnetars can produce both high-energy gamma flares and low-energy radio flashes? Are we witnessing different facets of a single physical process? Or is the magnetar merely a conduit for more exotic mechanisms, perhaps involving quantum electrodynamics, axion-like particles, or interactions with the dark sector? Indeed, magnetars push the boundaries of our physical theories into regimes we cannot replicate on Earth. The magnetic field strength near a magnetar exceeds the quantum critical limit, where even the vacuum becomes nonlinear, altering the behavior of light and matter in ways predicted only by quantum electrodynamics. At these field intensities, atoms deform into pencil-thin structures, and photons can split or merge in defiance of classical expectations. Some theorists posit that magnetars might be natural laboratories for new physics, offering glimpses into the behavior of matter at the intersection of general relativity, quantum mechanics, and extreme conditions. Others speculate that these stars might help probe the elusive nature of dark matter, acting as gravitational traps for exotic particles whose annihilations might subtly alter magnetar dynamics. We are far from understanding them fully. Like the Kuiper Cliff, magnetars represent a kind of frontier, a place where our models hesitate, where equations strain, where intuition fails. They are not the edge of space, but the edge of physical law. The contrast between the Kuiper Cliff and the magnetar enigma is striking. One is quiet, remote, spatially mysterious. The other violent, compact, temporally sudden, and yet they share something fundamental. Both sit at the boundary of our comprehension. One is a puzzle of absence, the other of excess. One challenges our understanding of gravitational dynamics in the outskirts of our solar neighborhood. The other tests our knowledge of matter and magnetism at nuclear densities. One pulls us outward, the other inward, and both whisper, in their own dialects, of a universe richer, stranger, and more dynamic than we dared imagine. They remind us that reality does not conform neatly to human expectation. They force us to question our frameworks, not to discard them, but to evolve them, to stretch them toward truths we have not yet glimpsed. These phenomena, though distant, reflect something deeply human. We, too, stand at a kind of boundary between knowledge and mystery, between comfort and curiosity, just as the Kuiper Cliff marks the outer limit of what we thought we understood about the solar system, and just as magnetars push the internal coherence of matter to breaking. So we live in a state of perpetual inquiry, straining toward insight with instruments and equations, but also with wonder and metaphor. The universe does not give up its secrets easily, and yet, through cliffs and flares, through silence and fury, it speaks to us still. In that speaking, we are reminded that science is not merely the accumulation of facts, but the cultivation of awe, that physics, at its most honest, is an act of listening, and that even in the perimeters of the known, there are echoes of something vast and unnamed, waiting to be felt. Hidden cores and missing elements. In the frigid twilight of the solar system, far beyond the rocky inner planets and the familiar gas giants, drifts a world that whispers secrets it refuses to yield. Uranus, a cyan orb suspended in the void, is often overlooked, quiet, cold, seemingly uneventful, yet beneath its serene surface lies one of the most profound enigmas of planetary science. Unlike Jupiter or Saturn, with their storms and swirling belts, or even Neptune, its deep blue twin, Uranus is eerily muted. It radiates almost no internal heat. Its thermal signature is so faint that the planet appears to emit less energy than it receives from the Sun, a stark contrast to its planetary siblings. This thermal silence suggests an interior unlike anything we've modeled, a core that may hold secrets not just about Uranus itself, but about the broader processes that shape the architecture of the solar system. And then, there is the tilt Uranus spins nearly sideways, its rotational axis lying almost in the plane of its orbit, like a planet tipped and forgotten. The cause may have been cataclysmic, a titanic collision in the solar system's youth, or the slow gravitational sabotage of unseen forces, sculpting its orientation over eons. This orientation has consequences: extreme seasonal cycles, a magnetic field misaligned from its core, and an interior structure that may be layered, chaotic, or fundamentally different from what we expect. We cannot peer directly inside, but we suspect that the core may be home to materials we barely understand. such as superionic ice, a state where water behaves as both solid and liquid, its ions moving like ghostly currents through a crystalline lattice. This strange form of matter, predicted in high-pressure simulations, may not only exist in Uranus but dominate its internal structure. If so, it challenges how we model conductivity, heat flow, and the very definitions of phase transitions under planetary conditions. And in this planetary riddle, this elegant silence of Uranus, we find a metaphor for a deeper mystery, one etched not in planetary behavior, but in elemental fingerprints cast across the entire cosmos, for scattered throughout the stars, in the hearts of galaxies and the halos of ancient stellar remnants, lies a mismatch that has troubled cosmologists for decades: the lithium problem. When the universe was but minutes old, it forged the first elements in a process known as Big Bang nucleosynthesis hydrogen, helium, and traces of lithium. The ratios of these elements were predicted with extraordinary precision, a rare success in cosmology's attempt to align theory with observation. And yet, as we look to the oldest stars, those ancient population tube beacons whose light carries the memory of primordial creation, we find far less lithium than we should. In some stars, the lithium abundance is a third of the expected value. In others, it's nearly absent. This is no small discrepancy. It's a fracture at the base of a model we otherwise trust, a problem that refuses to be soothed by statistical error or observational imprecision. The elements are the universe's memory. When one of them goes missing, it's as if part of our cosmic history has been redacted. So where is it? Some theories suggest that lithium is not truly missing, but hidden, burned away in the interiors of stars through mechanisms more subtle than we've accounted for. Perhaps convective mixing or atomic diffusion pulls lithium deep into stellar hearts, where it is destroyed in nuclear reactions and never reemerges. But this hypothesis struggles with uniformity. Why do so many stars, across such varied types and epochs, show the same unexpected shortfall? Could there be flaws in our nuclear physics, in the reaction rates assumed during Big Bang nucleosynthesis? Or are more exotic culprits at play? Some physicists have pointed fingers at hypothetical particles, axions, sterile neutrinos, or other dark sector interactions that might have altered the cooling rate of the early universe or shifted the balance of elemental synthesis. Others have speculated on asymmetric baryogenesis, time-varying constants, or alternative cosmologies that tweak the fundamental timeline of the early universe just enough to explain the discrepancy. These are not fringe ideas, but serious conjectures emerging from the space between theory and observation, from the tension that arises when a model elegant in its mathematics confronts a sky that refuses to conform. The lithium problem and Uranus's interior, seemingly unrelated, are bound by a deeper truth. They are reminders that science, for all its rigor, remains a human endeavor, fallible, fragile, always incomplete. Each model we build is a map, not the territory, a sketch drawn with the best instruments we possess, guided by the logic of mathematics and the humility of measurement. But some landscapes resist our gaze. Some truths remain just out of reach, like the icy pressure chambers deep inside Uranus, or the primordial reactions that lit the first fires of elemental birth. In both cases, we are left navigating by inference, reaching for understanding in the darkness between data points. And yet, it is in that reaching in, that stretching of theory toward anomaly, that science becomes most profound. It is not in certainty, but in doubt that discovery lives. To contemplate these mysteries is to confront a universe not built for our comprehension, but rich enough to reward our persistence. Uranus drifts in its orbital solitude, bearing scars of trauma and containing an interior that may hold new states of matter. Lithium whispers of a misremembered beginning. its absence questioning our confidence in the earliest pages of the cosmic story. Together, they speak of a cosmos where every silence is significant, every inconsistency a clue. We do not know if we will solve these puzzles in this century, or ever. Perhaps new missions to Uranus will finally dive into its atmosphere and pierce the veil of its interior. Perhaps future telescopes will refine our stellar models, or uncover new particles that restore lithium to its rightful place. Or perhaps, as often happens in science, the answer will come from an unexpected angle, a theoretical leap that reframes the question itself. Until then, we carry these anomalies like riddles folded into the star maps of our understanding. We look outward with eyes that seek symmetry, but find beauty even in asymmetry. We listen for the rhythm of reason, but are not afraid of dissonance, because somewhere in that dissonance lies the voice of the cosmos, still speaking, still singing, still waiting to be heard. Radio ghosts and dust veils, signals from the unknown, in the boundless dark between galaxies, where the thin fabric of space stretches in silence and the density of matter thins to near nothingness. There come flickers, faint, defiant flickers, not of light, not of structure, but of radio waves, ghostly whispers traveling unimaginable distances, haunting the cosmos with their slow, drifting rhythm. These are not the familiar crackles of pulsars or the burst patterns of known stars. They are slower, broader, stranger. They rise not from within the spiraling arms of galaxies, but from the peripheries of cosmic maps, from voids that should be silent. For decades, astronomers have cataloged strange radio emissions that seem to come from nowhere, flickering into the sensitive ears of radio telescopes with no matching optical source. Some drift in frequency, others persist without explanation, and a few arrive with such regularity that speculation drifts from the scientific to the speculative, from the realm of plasma and black holes to the eerie corridors of hypothetical technology and unknown cosmic actors. And yet, to leap to aliens is to skip the poetry of the question. What if these signals are the language of galaxies, speaking in tones we have only begun to understand? What if this radio static is the soundtrack of the void, a resonance of collisions, of magnetized plasma arcs, of dark matter interactions far beyond our current physics? Among the leading contenders for these ghost signals are active galactic nuclei, supermassive black holes at the centers of galaxies, cloaked in magnetic fury, that can send out collimated jets of energy stretching across millions of light years. These radio lobes, interacting with the intergalactic medium, can distort and scatter, creating echoes that outlive their source. Or perhaps the sources are dying stars in intergalactic exile, ejected from their galaxies by gravitational chaos, now pulsing their last messages across a vacuum no one was meant to hear. Some signals may even originate in galaxy cluster interactions when massive galactic bodies merge. The resulting plasma shocks can emit radio waves on scales that defy intuition. And yet, the true mystery lies in the ones that do not fit any known category. They do not repeat like pulsars. They do not flash like fast radio bursts. They drift, they linger, and then they vanish. They do not ask to be found. They simply exist, waiting to be noticed. And what of the veils? If radio signals are the voices of the void, then interstellar and intergalactic dust clouds are its silences. These clouds, composed of microscopic grains of carbon, silicates, and frozen gases, stretch across the Milky Way and beyond, scattering and absorbing light in ways that both reveal and deceive. They are born in the atmospheres of dying stars and the shock waves of supernovae, but they do not die quickly. Instead, They drift carried by the tides of galactic winds and magnetic fields, accumulating in dark filaments that stretch across the sky. To the naked eye, they are nothing, but to astronomers, they are distortions biasing the light from distant galaxies, muting the brightness of supernovae, reddening the colors of starlight. In the pursuit of precision cosmology, dust is the eternal contaminant, but it is also a storyteller. For inside those grains are chemical records of ancient furnaces, isotopic signatures of stellar deaths, and the raw material of future planetary systems. Dust is not just a nuisance, it is memory. It is the medium through which stars form and through which the light of the universe must pass. There are clouds vast and faint that defy classification. Cold, dark molecular clouds in the outer reaches of our galaxy harbor the seeds of future stars, yet others, high above the galactic plane, are so faint that they can only be seen when backlit by quasars or mapped by the dimmest of infrared echoes. These are the whispering veils of the universe, half visible, half imagined. Are they leftovers refused from galactic collisions, cast into the void like the spray of an ocean wave? Or are they the embryos of something new, nurseries not yet ignited, clumps of potential awaiting the right trigger? The answer remains as unclear as the clouds themselves. In every observation lies a distortion, in every correction, a new uncertainty, and still, we measure, we map, we model, we chase clarity through veils that shimmer and shift. It is humbling to know that some of the universe's greatest mysteries may not lie in what is distant or rare, but in what is faint, not in the spectacular bursts of gamma rays or the luminous death of stars, but in the slow pulse of radiostatic and the quiet glow of dust. These are the universe's margins, the things too dim to dominate, too subtle to ignore. They teach us that not all knowledge is bright, not all truths are loud. That in the quiet, in the veil, in the flicker, there is revelation, and in the search for meaning among the softest signals and the faintest shadows, we are reminded of the fragility of our vision, the limits of our models, and the beauty of a cosmos that will always remain partly unknown. So let us end not with certainty, but with reverence for the ghosts that drift between the galaxies, and the veils that drape the stars, for the silence that speaks, and the darkness that reveals. Let us carry these mysteries not as failures, but as invitations, to listen closer, to look deeper, to wonder longer, because beyond the reach of even our most sensitive instruments, the universe is still speaking in a language made of light and dust, signal and silence, knowledge and awe. And so we arrive at the end, or perhaps only the edge of the beginning, after venturing across ancient trails of stars and diving deep into galactic voids. After listening to the echoes of quasars and unraveling the magnetic tantrums of dying stars, we are left with something stranger than certainty's wonder. Not the kind of wonder born from answers, but from the realization that even the most precise instruments, the most elegant equations, and the most powerful telescopes are merely fingertips brushing the surface of a vast, unseen architecture. What have we found? Ghost streams whispering of ancient collisions, light bending to forgotten alignments, cosmic voids that repel galaxies like silent oars rowing through nothing, planets that refuse to radiate, elements that hide from our grasp, signals flickering from between galaxies, unclaimed by any known source, and dust everywhere, dust that dims and veils and guards the secrets of the stars. These are not just curiosities, they are messages. They are the universe leaning down and murmuring, "You do not yet understand me." But we try. With each anomaly, we expand the perimeter of the known. With each inconsistency, we are offered a portal into deeper laws. Science was never meant to be a fixed edifice. It is a raft in a storm, a melody played against silence. We do not map the cosmos to find comfort. We map it to remember that discomfort is a sign we are close to truth, that when a star vanishes without reason, or a polarization stretches across billions of light years, it is not failure, it is invitation. And behind all of it is time, time not just as ticking clocks or spinning orbits, but as a vast unfolding. These anomalies are fossils of motion, footprints in gravity, bruises left by forgotten giants. We are not outside this story. We are made of it. The lithium that should have been but isn't, the magnetar that screams once and dies, the rogue planet that drifts unloved through darkness. They are part of the same ledger that recorded your birth, your breath, your gaze upward on a cold night. A dense fog blankets the street, swallowing sound and light, as if the world has paused its breath. On a cold, moonless night, you step onto the road, unaware of the headlights slicing through the mist. A car surges forward, too fast, too close. Your heart lurches. But before impact, a force, a stranger's hands, shoves you aside. You stumble, safe, as tires screech and a body collapses onto the tarmac. An elderly figure, crumpled and still, has traded their life for yours. Later, in the quiet of a police station, an officer hands you an envelope, its edges worn, addressed to you in unfamiliar script. Inside, a note, just 2 words. Study physics. Who wrote it? Why did they save you? The mystery clings like the fog, pulling you toward a life reshaped by those words, toward a destiny entwined with the enigma of time itself. That night lingers, a wound and a gift, as you dedicate yourself to physics, chasing the secrets of the universe. Decades pass, and you stand celebrated, a professor unraveling Albert Einstein's theories of relativity. Time, you learn, is not a straight line but a fabric, woven with possibilities that defy intuition. Your obsession narrows to one question: can we travel through time? In your laboratory, surrounded by humming machines and scribbled equations, you crack it. The world's first time machine glows before you, its soft buzz a siren call. And then, clarity strikes like lightning. You pull the framed note from your wall, the one you've kept all these years, and slip it back into its envelope. Stepping into the machine, you set the dials to that misty night, knowing what you must do. You arrive just in time to push your younger self from the car's path, feeling the impact as the world fades. Your life ends where it was saved. But who wrote the note? It's a question that haunts, a paradox with no clear answer. You carried it back, but you received it first. It exists, creatorless, caught in a loop, a relic that seems to defy origin. This is the bootstrap paradox, a riddle where an object or idea circles through time, its beginning lost in the endless cycle. Did you choose to study physics, or was it always destined? The note's command feels like a whisper from nowhere, a thought born without a thinker. This is the ex nihilo paradox, where ideas emerge without a source. And what of your choice to step into the machine? If you hadn't, you'd have died young, never reaching this moment. Your path seems fixed, unchangeable, a thread in a tapestry already woven. This is the predestination paradox, suggesting your free will is an illusion, your future as set as the past. Imagine time as a river, vast and unyielding, carrying us from the Big Bang's foothills to the universe's distant end. We drift downstream, unable to paddle back or speed forward. Yet the river's source and mouth exist together, unchanging. Yesterday doesn't vanish, just as the riverbed doesn't dissolve behind us. Tomorrow isn't conjured from nothing. It's already there, as real as today. This is the block universe, a concept rooted in Einstein's work, where past, present, and future coexist in a single, four-dimensional tapestry. Your great-grandparents laugh upstream. Your descendants dream downstream, all as real as you are now. This idea, called eternalism, clashes with presentism, the belief that only the present exists, the past gone and the future unborn. Philosophers have wrestled with this since ancient times, but Einstein's relativity gives eternalism weight, painting time as a landscape we traverse, not a fleeting moment. Picture yourself in a canoe, gliding through a jungle river, howler monkeys calling from the trees. The current pulls you forward, no effort needed, but you can't turn back. This is how time feels, relentless, unidirectional. Yet the river's upper reaches don't disappear just because you've passed them. They're still there, out of sight. Similarly, the block universe suggests the past endures, not as memory, but as reality. Einstein's special relativity, published in 1905, shattered the idea of absolute time. There's no universal clock ticking the same for all. Time bends, stretches, depending on how you move through space. One person's now can be another's then. Events shuffling like cards depending on your perspective. If my yesterday is your tomorrow, how can the past simply vanish? It must persist, woven into the fabric of space-time. Space-time, a term coined by Hermann Minkowski in 1908, unites space and time into one entity. Imagine it as a vast sheet stretching across the cosmos, where every event, your birth, your first kiss, your final breath, has a place, marked by 3 spatial coordinates and 1 temporal. A stationary object's mark moves only through time, second by second, tracing a line through this block universe. This line, your world line, maps your journey from cradle to grave. Every particle in your body follows its own world line, weaving together to form you, a knot in space-time's fabric. As you eat, breathe, or age, new particles join, others depart. But your path is fixed, unchangeable. The block universe is like a novel, its pages written, your choices already inked. You can't stray from the plot, just as a train can't leap its tracks. Now consider the paradoxes again. If you're destined to invent the time machine to save your younger self, where does the cycle begin? The letter loops endlessly, but does it age, growing tattered with each pass? This is the restoration paradox, questioning whether objects in a time loop degrade or endure, and what if you hesitate? Could you refuse to step into the machine, letting your younger self die? Logic falters here. If you don't save yourself, you'd never reach this moment to refuse. This is the auto-infanticide paradox, suggesting you can't undo your own existence. These riddles twist the mind, revealing time's complexity. The block universe, with its fixed paths, implies a destiny we can't escape. Yet the idea of looping back to rewrite our story tantalizes, a promise of control over the uncontrollable. Einstein's general relativity, unveiled in 1915, deepened this vision. It describes gravity not as a force, but as space-time's curvature. Picture space-time as a trampoline, sagging under the sun's weight, forming a gravity well. Planets roll through this dip, their paths curved by the fabric's shape. Mercury, closest to the sun, feels this curvature most, its orbit wobbling in ways Newton's laws couldn't explain. In 1859, astronomer Urbain Le Verrier puzzled over Mercury's odd path, suspecting a hidden planet. None was found. Einstein's equations solved the mystery, showing how space-time's curve, not a new planet, caused Mercury's precession. This triumph, announced in a letter to David Hilbert, proved general relativity's power, revealing gravity as geometry, not a pull. Space-time bends, and we move with it. Our world lines tracing paths through a universe where all moments coexist. Tests of relativity multiplied. During a 1919 solar eclipse, light from distant stars bent as it passed the sun, confirming spacetime's malleability. Gravitational waves, ripples in this fabric, were detected in 2015, further proving Einstein's vision. Black holes, swirling vortexes of curved spacetime, bend light and time alike. These discoveries paint a cosmos where past, present, and future sit side by side, a block universe where every event is eternal. But if time is a river and we can't paddle upstream, how do we visit the past? The block universe suggests it's there, as real as now, but reaching it demands bending spacetime itself. Your time machine, born from years of study, is the key, but its use raises questions. Did you choose to build it, or was it always meant to be? As you stand before your machine, the note in your pocket, the weight of that misty night presses close. You've lived a life shaped by a stranger's sacrifice, driven by two scrawled words. Now, you understand the stranger was you, older, returning to close the loop, but the paradoxes linger. Who authored your path? Was it ever yours to choose? The block universe holds your story. Every moment fixed, yet the possibility of stepping into the machine, of rewriting a moment, feels like freedom. The river of time flows on, carrying you toward a destiny already written. Yet the chance to loop back, to touch the past, whispers of a universe where endings are beginnings. As you set the dials, the hum of the machine fills the air, and the fog of that long-ago night seems to rise again, waiting for you to step through. The hum of the time machine fades, but its echo lingers in your bones, a reminder of the night you stepped through time to save yourself. Now, standing in the quiet of your laboratory, you wonder, can you truly outrun time, or are you merely chasing its shadow? The block universe holds every moment past, present, future, like stars fixed in a cosmic tapestry. Yet the urge to leap forward, to glimpse tomorrow, burns bright. What would it mean to visit the future, to see the world beyond your years? The river of time carries you forward, its current relentless, like a canoe gliding through a jungle's humid embrace. Howler monkeys calling from distant trees. You can't paddle back, but what if you could speed ahead, skipping decades like stones across water? The idea feels intoxicating, a chance to witness your descendants' lives or the universe's far-off chapters. Einstein's theories, the ones you've spent your life unraveling, suggest it's possible. Special relativity, born in 1905, reshapes time itself. It tells us there's no universal clock, no single now shared by all. Time stretches, contracts, depending on how fast you move through space. A traveler racing near light speed spends less time in motion, as if hoarding seconds while the world ages swiftly. This is relativistic time dilation, a key to the future. Picture a particle, a muon, born high in Earth's atmosphere, sparked by a cosmic ray's violent collision. These muons, unstable flecks of existence, should decay in a mere 1.56 millionths of a second. Racing at 98% of light speed, they plummet toward the ground. Yet far more reach it than should. Why time slows for them? From their perspective, fewer half-lives pass, as if they're cheating decay itself. In 1938, physicist Bruno Rossi, high in the Rockies at Echo Lake, measured these muons. His instruments, perched 2,300 meters above sea level, captured their strange survival. The muons were time travelers, skipping forward in a way that Rossi's calculations confirmed. Their journey, fleeting yet profound, proved that time bends for those who move fast enough. Imagine yourself as that muon, not falling to Earth, but looping through the cosmos at near-light speed. You embark on a 25-year journey, your spacecraft a speck against the stars. When you return, you're 25 years older, but Earth has aged 125 years. Your friends, your family, are gone, replaced by their grandchildren's grandchildren. The world you knew is a memory, its skyline reshaped, its stories faded. This is no paradox but a fact, woven into relativity's fabric. Time dilation doesn't just bend time, it reshapes lives. Consider the Kelly twins, NASA astronauts, Mark and Scott, born 6 minutes apart. Scott, spending months aboard the International Space Station, moved faster through space-time than Mark. Those extra days in orbit at speeds dwarfing a car's stretched time's flow. Mark, earthbound, aged fractionally more. By their reunion, Mark was 6 minutes and 5 milliseconds older, a gap widened by time's malleability. This effect, though small for astronauts, grows vast at extreme speeds. A traveler at 99.99% of light speed would weigh as much as a rhinoceros, their mass swelling with energy. As Einstein's equation, energy equals mass times the speed of light squared reveals. Accelerating them would demand the energy of entire nations, a feat far beyond our grasp today. Yet, even on Earth, time dilation whispers its presence. Climb a mountain, like Rossi did, and you edge out of Earth's gravity well, where space-time is less curved. Time ticks slightly faster there. Atomic clocks, precise to a 15 billionth of a second per year, prove it. In 2022, physicists placed 2 such clocks a mere millimeter apart in height. The higher clock ran faster, its ticks outpacing the lower, confirming gravitational time dilation. Time, it seems, is not just relative to speed, but to gravity's pull. Gravity warps space-time, bending it like a sheet under a heavy stone. Near a massive object, like the Sun, space-time curves deeply, forming a gravity well. Planets trace paths through this dip, their orbits shaped by its contours. Mercury, plunging closest to the Sun, feels this curvature most, its path wobbling in ways Newton's gravity couldn't predict. In 1859, Urbain Le Verrier puzzled over this, suspecting a hidden planet. None was found. Einstein's general relativity, published in 1915, solved the riddle. In a letter to David Hilbert, Einstein wrote of deriving Mercury's perihelion motion, a triumph no other theory had achieved. The Sun's gravity well, curving space-time, caused Mercury's orbit to precess, proving gravity is not a force, but a geometric dance. This curvature offers another path to the future. Enter a deep gravity well, like that of a supermassive black hole, and time slows for you. Spend a year near its edge, carefully avoiding its pull, and return to find Earth centuries older. This idea, explored in the film Interstellar, hinges on general relativity's truth. Space-time's shape dictates time's flow. Even on Earth, GPS satellites feel this. Orbiting high above, they move faster and sit in a shallower gravity well than we do. Their atomic clocks, ticking at a different rate, must be adjusted to sync with ours. Without this correction, your phone's navigation would falter, lost in time's subtle shifts. These experiments, muons, astronauts, clocks confirm time travel to the future is real, a scientific fact woven into the universe's fabric. But what drives this possibility? The block universe, where all moments coexist, suggests the future is already there, waiting. Your world line, the path you trace through space-time, stretches from birth to death, every choice mapped out. If you could leap forward, you'd land on a page already written, your descendants as real as you are now. The block universe, born from Einstein's relativity, paints time as a landscape, not a fleeting moment. Philosophers call this eternalism, opposing presentism's claim that only now exists. Eternalism sees your great-grandchildren living downstream, as vivid as your ancestors upstream. Time travel to the future, then, is less about creating tomorrow than visiting it, stepping into a moment already etched in space-time's block. Yet, the human cost lingers. To leap forward, you'd leave behind all you know. Imagine returning to a world where your loved ones are dust, their stories faded into history's pages. Ken Liu's story, Memories of My Mother, captures this ache, where a time traveler's journey disrupts family ties, generations slipping out of sync. The future beckons, but it demands sacrifice. You'd need a vessel to rival a muon's speed or a black hole's gravity, feats that dwarf our technology. The energy to propel a human near light speed equals months of global consumption. A barrier as real as the stars. Still, the possibility hums, like your time machine, promising a glimpse of tomorrow's light. As you stand in your laboratory, the note from that misty night in your hand, you feel the weight of time's river. You've saved your younger self, closed the loop. But the future calls, a horizon both distant and near. The block universe holds it all, your past, your now, your yet to come, yet the urge to leap forward, to see what lies beyond, stirs within. The muons, the clocks, the stars all whisper it's possible. Time, bent by speed or gravity, can carry you to a world not yet born. But what would you find there? A new dawn, or a shadow of what you've left? The river flows on, its currents pulling you toward answers that lie just out of reach. In a universe where every moment waits, eternal and alive. The laboratory is silent, save for the faint hum of your time machine, its dials glowing like stars against the dark. You've glimpsed the future's promise, the way time bends under speed or gravity, carrying you to tomorrow's already written. But what of yesterday? Can you step back, not just to save yourself, but to touch the past, to rewrite a moment lost in the river of time? The block universe holds every instant your first breath, a forgotten laugh, the night you were saved etched in space-time's eternal fabric. If the future is reachable, why not the past? The river of time, vast and unyielding, seems to flow one way, carrying you from the Big Bang spark to the universe's quiet end. Yet the past doesn't vanish, just as the river's source remains, hidden beyond the bend. Einstein's relativity, the foundation of your life's work, suggests the past is as real as now, a place you might visit if you could bend the rules of space-time. But how the future yields to speed or gravity's pull. But the past demands something more, a way to tilt the river backward, to paddle upstream against its relentless current. In 1937, a young Dutch physicist, Willem Jacob van Stockham, peered into this possibility. His paper, dryly titled "The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry," hid a revolutionary idea, Einstein's equations. He showed allow closed time-like curves, paths through space-time that loop back, letting your world line, the thread of your existence, intersect itself at an earlier point. A pensioner could revisit their childhood, or you could return to that misty night, pushing your younger self from harm. On paper, Nothing in general relativity forbids this. Your time machine, buzzing in the laboratory, is proof it's possible. But Van Stockham's work hinted at a catch to loop back. You might need to travel faster than light, to step outside your light cone, the boundary of all paths you could take. Imagine standing still, your world line stretching forward through time. Light, racing at 300,000 kilometers per second, sets the limit of where you can go. 1 second from now, you can't be more than 300,000 kilometers away. 2 seconds, 600,000. This boundary forms your light cone, a funnel of possibility widening with time. To reach the past, your world line must curve back, crossing an earlier point. But to do so, you'd need to escape this cone to move faster than light itself. Einstein's special relativity, born in 1905, declares this impossible. The faster you go, the heavier you become. Your mass, swelling with energy until accelerating further, demands an infinite force. Light speed is the cosmic wall, unbreakable for anything with mass. In 2011, a flicker of hope emerged. Physicists at the Opera experiment, buried beneath Italy's Gran Sasso mountain, announced a shock neutrinos, ghostly particles fired from CERN 730 kilometers away, seemed to arrive 60 nanoseconds too soon. If true, they'd traveled faster than light, shattering Einstein's barrier. The news rippled through the scientific world, promising a path to the past. A neutrino, moving faster than 300,000 kilometers per second, could tilt its world line back, looping through spacetime. But by 2012, the dream faded. Faulty equipment, not superluminal speed, explained the anomaly. The light speed wall held firm, closing one door to the past. Yet other paths remained, hidden in spacetime's folds. What if you could tilt your light cone without breaking light speed? In 1974, physicist Frank Tipler imagined a way. Picture a cylinder, 10 times the sun's mass, spinning billions of times a minute. Follow a precise spiral around it, and its immense gravity warps space-time, tilting your light cone backward. Your world line, confined within this cone, could loop to an earlier moment, carrying you to the past. Tipler's cylinder, though, was no practical machine. It needed to be infinitely long, a mathematical ideal far from reality. Even a finite version would require vast negative energy, a concept from quantum mechanics where empty space teems with virtual particles, briefly dipping energy below zero. These fleeting bursts, like an overdraft from the universe, couldn't sustain a human-sized time loop. The past, tantalizingly close, remained out of reach. Another possibility emerged, one that didn't demand impossible speeds or infinite cylinders. In 1985, Carl Sagan, crafting his novel Contact, sought a way to send a traveler to the star Vega, 25 light-years away, without breaking light speed. He called physicist Kip Thorne, who suggested a wormhole. Picture spacetime as a sheet. Earth at one end, Vega at the other. Fold the sheet, bringing the points together, and a wormhole forms a tunnel through spacetime's fabric. Step through, and you're at Vega instantly, without crossing the vast distance. From outside, it looks like faster-than-light travel, but you've merely taken a shortcut. Thorne realized wormholes could bridge time as well. Drag one mouth of a wormhole on a near-light-speed journey, and time dilation slows its clock. Return, and the mouths differ in age. Enter the younger mouth, exit the older, and you're in the past. But wormholes are fragile. Gravity from a passing object could snap them shut. To keep one open, you'd need negative energy again, or perhaps exotic forces like quantum entanglement or magnetic fields. In 1985, J. Richard Gott and William Hiscock explored cosmic strings, hypothetical threads of immense density left from the universe's birth. Tracing a precise path along two cosmic strings, you could tilt your light cone backward, looping to the past without exceeding light speed. Quantum entanglement, linking particles across vast distances, also hinted at superluminal connections. But transferring data or people this way proved impossible. Each path cylinders, wormholes. Cosmic strings offered theoretical doors to the past, but none were practical. The block universe, with its fixed moments, seemed to taunt you, holding the past just beyond your grasp. Yet the past's allure persists. Imagine stepping through a wormhole, emerging on that misty night, not to save yourself, but to see your parents young, to walk streets long changed. The block universe says those moments exist, as real as now. Your world line, woven through space-time, could loop back, but the paradoxes loom. If you returned and changed the past, would you unravel your present? The bootstrap paradox. Your note. Circling without origin suggests a closed loop. But what if you refuse to write it? The predestination paradox whispers that you can't refuse. Your actions are fixed, written in space-time's book. The auto-infanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge free will itself. Was your choice to build the time machine ever yours? The river of time, with its eternal past and future, holds these questions. You've seen the future's possibility, confirmed by muons and clocks. The past, though, demands more a bending of spacetime's rules, a tilting of light cones. Van Stockham, Tipler, Thorne, and others map the path, but each requires feats beyond our reach. Infinite cylinders, stable wormholes, cosmic strings. Yet the block universe insists the past is there, waiting. As you stand before your machine, the note in your pocket, you feel the pull of yesterday. Could you step back, not just to close a loop, but to live a moment again? The river flows, its waters holding every memory, every regret. The hum of the machine grows louder, inviting you to chase the past, to seek answers in a universe where time, though fixed, whispers of possibilities yet untraveled. The laboratory air feels heavy, charged with the weight of questions unanswered. Your time machine, its soft glow, a beacon in the dim, hums with the promise of the past, a past you've touched once, saving yourself, but now yearn to explore further. What if you could rewrite a moment, undo a regret, only to find the universe splintering beneath your choice? The river of time, eternal and unyielding, holds every yesterday, but quantum whispers suggest its currents might fork, offering paths where paradoxes dissolve. The block universe, that vast tapestry of space-time where all moments coexist, paints the past as real as the present. You've seen how speed and gravity bend time, letting muons and astronauts slip into the future. The past, though, demands a steeper price, curving spacetime's fabric to tilt your light cone backward, looping your world line to an earlier day. Einstein's equations, your life study. Allow it through closed time-like curves, paths that circle back like the note you carried to that misty night. But the paradoxes, bootstrap, predestination, auto-infanticide haunt you. If you change the past, do you unravel your now? Quantum mechanics, the strange realm of the subatomic, offers a way out. A vision where time's river splits into countless streams, each a new reality. Picture yourself in a stark room, wrists bound by cold steel, sweat tracing paths down your face. Before you, a glass vial of lethal gas sits beside a hammer, its robotic arm linked to a machine measuring subatomic particles. Each particle can be in one of two states, A or B, a 50-50 chance. If it's A, you live. If B, the hammer falls, the vial shatters, and you die. The machine will measure 100 times before your release. The odds of surviving all 100 are 1 in a million trillion trillion, a number so vast it dwarfs the stars. Your heart pounds as the first measurement clicks. A, you breathe. The second, A again. By the 10th, hope flickers. By the 99th, you're dizzy with disbelief. The final click A, you're free, alive against impossible odds. This is no mere luck. It's a glimpse into the many worlds interpretation, a quantum theory that reshapes time's possibilities. In 1957, physicist Hugh Everett III proposed this idea: every quantum event with multiple outcomes splits the universe. When the machine measures A or B, reality fractures one world where you live, another where you die. After 100 measurements, 100 branches form, and in one, you survive, marveling at your fortune. In 99 others, you perish, each branch a different fate. This is the quantum immortality experiment, a human echo of Schrödinger's cat, where a feline in a box is both alive and dead until observed. Quantum mechanics says the particle exists in a superposition, both A and B, until measured. And so do you, alive and dead until the universe chooses. But Everett's many worlds theory says it doesn't choose. Every outcome happens, each in its own reality. This fracturing universe, a tree of infinite branches, offers a solution to time travel's paradoxes. Consider the grandfather paradox: you travel back. Kill your grandfather as a child, preventing your mother's birth, and thus your own. How? Then, are you here to kill him in the block universe with its fixed world lines? This seems impossible. Stephen Hawking's chronology. Protection conjecture argues the universe forbids such trips, guarding cause and effect. Igor Novikov's self-consistency principle agrees, saying you can visit the past but not change it. Try to shoot your grandfather, and the gun jams, or you miss. Your actions, already written, can't rewrite the page. But these ideas falter in complex cases, like the one posed by physicists Barak Shoshani, Jared Wogan, and Jacob Hauser between 2020 and 2022. Imagine a time machine and a set of balls, each either black or white. When two balls meet, they swap colors. A black ball turns white, a white one black. A black ball enters the time machine, emerges in the past, and collides with its earlier self. The collision turns both balls white. The older ball, now white, loops back through the time machine again. But here's the paradox. The same ball exits the same machine at the same moment. Yet it's black the first time and white the second. Novikov's principle can't resolve this. How can the ball be two colors at once? The many worlds theory, though, offers clarity. The black ball starts in time stream A, emerges in time stream B, and collides with its past self. In this new stream, the other ball loops back, not the first. The paradox dissolves because the ball's journey spans different realities, not a single, contradictory loop. This idea frees you from the grandfather paradox. Travel back, kill your grandfather in time stream B, and your existence in time stream A remains untouched. Your mother, your birth, your life all safe in the original stream. Free will returns. You can choose without unraveling your past. The bootstrap paradox. 2 finds an answer. The note you carried to that misty night, seemingly authorless, might originate in another stream. In time stream A, you write it. Travel to time stream B and give it to your younger self. They, in turn, grow up, build the time machine, and carry the note to time stream C. The loop persists, but its origin lies across realities, not in a single, creatorless cycle. The ex nihilo paradox ideas like study physics appearing from nowhere fades as each stream provides a source, a writer in another world. But this solution carries weight. If every quantum event splits reality, the universe fractures endlessly. Every choice, every particle's flicker, spawns new streams. As physicist Bryce DeWitt said, every quantum transition in every star, every galaxy, splits our world into myriad copies, an infinite array of views, each slightly different. Lives every possible life, some where you're a poet, others a president, others never born. John Wheeler, who coined wormhole, grew wary of this, calling it laden with metaphysical baggage. Yet the many worlds theory gains followers, its logic untangling time's knots. Your note, your machine, your choice to save yourself, they ripple across streams. Each reality a new verse in time's endless song. The block universe, with its fixed world lines, seems rigid, yet quantum mechanics suggests flexibility. Closed time-like curves, wormholes, cosmic strings all hint at paths to the past, but they demand exotic conditions, negative energy. Infinite cylinders, or stable tunnels through space-time. Quantum entanglement, linking particles across vast distances. Teases superluminal connections, but data can't travel that way. Still, the many worlds theory softens these barriers. If you step through a wormhole to the past, you emerge in a new stream, free to act without breaking your origin. The river of time, once a single flow, becomes a delta, its waters splitting into countless channels, each holding a different story. As you stand before your time machine, the note in your pocket feels heavier, its words a bridge between worlds. You've saved yourself once, closing a loop, but the past calls again, not just to repeat, but to explore. Could you visit a lost moment, see a loved one smile, without shattering your now? The many worlds theory whispers yes, offering a universe where every choice branches, where paradoxes dissolve into new realities. The laboratory's hum grows louder, the dials glowing with possibility. Time's river, vast and eternal, splits before you, its streams shimmering with lives unlived, moments unmade. You step closer, drawn to the promise of yesterday, wondering which world awaits your next leap. The glow of the time machine flickers in the laboratory, a silent witness to your journey through time's vast river. You've chased the future, glimpsed the past, and felt the universe splinter into countless streams, each holding a version of you. Now, standing at the edge of this moment, you wonder, what does it mean to live in a cosmos where every instant is eternal, where every choice echoes across realities? The note in your pocket, worn by years and loops, whispers the answer. Time is both your cage and your freedom. The block universe, that four-dimensional tapestry where past, present, and future coexist, holds your life's story, from the misty night you were saved to the hum of the machine before you. Einstein's relativity, your life's work, reveals time as a landscape, not a fleeting moment. Your world line, the path tracing your existence, weaves through this landscape, fixed yet full of possibility. You've seen how speed and gravity stretch time, letting muons and astronauts slip into the future. You've explored paths to the past, closed time-like curves, wormholes, cosmic strings, each a theoretical bridge to yesterdays as real as now. The many worlds theory, with its branching realities, untangles paradoxes, letting you rewrite moments without unraveling your origin. But what does this mean for you? a knot of worldlings navigating an eternal cosmos. Picture the river of time, its currents carrying you from the Big Bang spark to the universe's distant end. You're in a canoe, gliding through a jungle's humid embrace, howler monkeys calling from unseen trees. The river's source, its bends, its estuary all exist together, unchanging. Your great-grandparents laugh upstream. Your descendants dream downstream, each as vivid as you are now. This is eternalism, the idea that all moments are equally real, opposing presentism's claim that only now exists. Philosophers like St. Augustine, in the 4th century, saw the present as a knife's edge between a lost past and an unborn future, but Einstein's general relativity, unveiled in 1915, paints a different picture. Time and space, woven into space-time, bend under gravity's weight, forming a block universe where every event, your birth, your choices, your end, is already written. Your world line, a thread in this tapestry, maps every step, from the breakfast you'll eat tomorrow to the day you'll marry. Every action is etched, unchangeable. The block universe is a book, its pages fixed, your choices pre-written. The note you carried back to that misty night, saving your younger self, was always part of the story. You didn't choose to study physics. The note, looping through time, ensured it. This is the predestination paradox, suggesting free will is an illusion. You built the time machine because you had to, because an older you already saved the younger, closing a loop that never began. The bootstrap paradox haunts you too. The note, creatorless, circles endlessly. Its origin lost in the river's flow. Does it age, growing tattered with each loop? The restoration paradox asks this, while the auto-infanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge the very notion of choice. Yet, the many worlds theory offers freedom. Each quantum event, each flicker of a particle, splits reality into streams. In one, you wrote the note. In another, you received it. In one, you saved yourself. In another, you hesitated. The grandfather paradox dissolves. You can kill your grandfather in a new stream, leaving your origin untouched. The ex nihilo paradox fades. The idea to study physics has a source across realities. Your time machine, buzzing before you, could carry you to a new stream where choices reshape outcomes. But this freedom comes at a cost. As physicist Bryce DeWitt said, every quantum transition in every star and galaxy splits our world into myriad copies. An infinite array of yous' lives, every possible life, some triumphant, some tragic, some never born. John Wheeler, who named the wormhole, called this metaphysical baggage, yet its logic untangles time's knots. The river of time, once a single flow, becomes a delta, its waters branching into countless channels. You're not just a passenger, but a chorus of selves, each singing a different verse. Time travel to the future, proven by muons and atomic clocks, is a fact. Astronauts like Scott Kelly, aging fractionally less than his twin, confirm it. GPS satellites, ticking faster in Earth's shallow gravity well, rely on it. The past, though, is less certain. Closed time-like curves, like those Van Stockham proposed in 1937, allow it on paper. Wormholes, suggested by Kip Thorne for Carl Sagan's Contact, offer shortcuts through space-time's folded sheet. Cosmic strings, imagined by J. Richard Gott, tilt light cones backward, but each demands exotic conditions, negative energy, infinite structures, or stable tunnels beyond our grasp. Quantum mechanics, with its virtual particles and fleeting negative energy, hints at microscopic time loops, but scaling them for a human remains a dream. Still, the past feels close. You've touched it once, saving yourself. But the urge to return persists. Imagine stepping through a wormhole, not to that misty night, but to a quieter moment, a childhood afternoon. Your mother's laugh, a world before loss. The block universe says it's there, as real as now. But the paradoxes linger. If you change a moment, do you split the universe, creating a new stream? The many worlds theory says yes, freeing you to act without breaking your past. Yet, each action spawns new realities, an infinite cascade of yous. The note in your pocket, its ink faded, feels like a relic from another stream, a message from a self you'll never meet. Was it ever your choice to follow it, or was it written in the stars? Time travel, whether forward or back, reshapes not just moments, but meaning. To leap forward, you'd leave loved ones behind. As Ken Liu's Memories of My Mother shows, where a traveler's journey fractures family ties. To visit the past, you'd risk splintering reality. Each choice a new world. The block universe, with its fixed world lines, suggests you're a character in a finished book. Yet quantum mechanics offers a multiverse where every page branches. Your time machine, a bridge between these truths, hums with possibility. You've lived its proof, saving yourself, but the cost weighs heavy. Each trip, each loop, echoes across streams, reshaping who you are. The river of time, eternal and vast, holds every version of you, past, present, future, each a knot in spacetime's wave, unraveling and reforming with every choice. As you stand before the machine, its glow soft against the laboratory shadows, you feel the river's pull. The note, tucked in your pocket, is both anchor and sail. You've traveled its loop, closed its circle, but the universe is wider now. Its streams infinite. Time travel, once a dream, is your reality. Yet it asks more than it answers. Are you free or fated? Do you write your story or merely read it? The block universe holds every moment, every you, in its embrace. The many worlds theory offers countless paths, each a life unlived. As the machine's hum fades, you step back. The note's words study physics echoing in your heart. Time's river flows on, its waters shimmering with every possibility, every regret, every hope, leaving you in awe of a cosmos where all moments, all selves, are eternal.